So in this chapter, we're going to do something called a two-sample test. In chapter 26, we took a sample and we compared that sample to some value. So just a quick review of chapter 26. We had a box and we think we know what's in there, or somebody says they know what's in there. Okay, so they say the average height of all men in the United States is 70 inches. Okay, now where did that number come from? It came from another study, or it came from some kind of estimation, or somebody just picked it. Oh, what? Oh, yeah. Okay, got it. Thanks. Um, so we just assume that this 70 inches is true. Okay, it involves way too many males for us to run around and check. We don't know what the standard deviation is, but we can check to see if we think that number is reasonable. So we run out and we do a study. So we talk to a whole bunch of people, say 625 people, and we get an average of 71 inches with an SD of 6. And then I create an SE, whatever that is, and I draw my normal curve, and I put 70 in the middle, and up here is my 71, and I calculate my z-score by taking 1 inch and dividing it by the SE, and I get a z-score which I turn into a p-value. Let's just say my z-score is 2.1, which gives me a p-value of about 3%. And again, I'm making all this up. What does this 3% tell me? That's the area to the right of 71 inches. Does a p-value equaling 3% say that 70 is probable or not probable? If my area is 3%, I reject the null. The null says the true value is 70. Are you guys confused? No? Okay. So the null says 70 is the real value, and the alternative says the real value is bigger than 70. I create my z-score of 2.1. I shade norm. I get a p-value of 3%. That's probably a little high, but whatever. And this tells me that this number is not likely to be correct. We reject the null and we say probably not. I almost marked you absent. Then I remembered. Okay, that's chapter 26. Does everybody get that? Okay. Well, the problem with chapter 26 is, where did this number come from? And sometimes it was the average for a country, and then we looked at like the average for a particular college or something like that. More likely, what you're going to do is two separate samples. Okay? And then you're going to compare those two samples to each other. Does that make sense? So in Taylor's wisdom teeth study, and we're going to make it a little bit more simple. Okay? Taylor goes and gets his wisdom teeth out, and they're divided into two groups. One group gets a placebo, which means they take a pill with nothing in it. Right? It's just a sugar pill that has no drugs in it whatsoever. The other group gets the pill that they want to study. And then the doctors, after the research is done, compare, were the people who took the placebo in more pain than the people who took the painkiller? Okay? So which of those two goes in the center of my normal curve? Right? So we're used to doing this. And we put one average here, and then I put my other average wherever it lands. Okay? But if I do two samples at the same time, which one goes in the middle? And the answer is neither of them. Because neither of them are assumed to be correct. The point is to compare them and see if they're different. So here's what we do. Let's say that I have a box of tickets, and in my box, the average of all my tickets is 7, and let's say I have 1,000 tickets. My average is 7, and the SD is 4. And you have a ticket, or a box, with 5,000 tickets in it, and your average is 6, and your SD is 3. Okay? Well, what happens when I draw from my box? Well, let's say that I draw 400 tickets out of my box. What is my expected value for average? If I draw 400 tickets out of my box, what is my average supposed to be? It's going to be 7. 7 plus or minus what? The SE. Which SE am I going to use? SE average, because this is an average. So I take 4 and I divide it by the square root of 400, and I get plus or minus 0.2. What does that mean? Going back to, this is chapter 5 stuff. What does 7 plus or minus 0.2 tell me? It means 68% of the time, anybody who plays this game will be between 6.8 and 7.2. Right? So if I were to draw my curve, here is 7, here is 7.2, and here is 6.8. If lots of people draw tickets out of my box without replacement, 68% of those people will have an average between 6.8 and 7.2. Okay? This is a probability. We know what's in the box. We're predicting what happens in the future. I have a 68% chance of landing in that window. Okay? Well, what if you draw 225 times out of your box? So you draw 225 times. What is your expected value for the average? 6. Plus or minus what? 3 divided by the square root of 225 is 15. And yours is also 0.2. So if we draw your curve, you're expected to get 6, but you have a 68% chance of getting between 5.8 and 6.2. Now, notice, our boxes are not the same size. They don't contain the same tickets. In fact, they can be totally different boxes, right? If these were people, the people in my box might not be in your box at all, or they might be. As long as they're independent, as long as the draws are independent, it doesn't matter. Okay. And we're not even doing the same number of draws. Okay. Well, we're going to make a new prediction, and this is what chapter 27 does. We are going to predict what happens when people draw from my box, and then you subtract the values of people drawing from your box. So we're going to compare, how do my results differ from your results? Okay. Do we expect the people that draw from my box to get the same results as people who draw from your box? No, it will happen, probably. Will anybody who draws from my box get 6.2? It could happen. It's pretty unlikely, but it could happen. So I'm going to do my probability session, and you're going to do yours, and we're going to calculate how different are those results. Okay? How do you do that? Well, the first part is easy. Expected value for the difference. That's just going to be the expected value from my box minus the expected value from your box, which is 7 minus 6, which is 1. So if a whole bunch of people draw from my box and a whole bunch of people draw from your box, and we take your average and we subtract it from my average, that number should be 1, right? So my expected value is 1. The tricky part is 1 plus or minus what? So we have two options that are immediately available. First is, what if we just add those two together? Because this is the difference from my box, and this is the difference from your box, the standard error from your box. So if we subtract the two, we're just going to combine the two differences into one. And it turns out that doesn't work. Okay? It turns out that that number is too big. The other option is to find the average between those two, and I wish they were different. Let's pretend that this is a 0.3, just for fun. So one option is to add them together, and we get 0.5. And we would say 1 plus or minus 0.5. But it turns out that if you do that, 0.5 is actually larger than the correct SE for the difference. Okay. The other option is to take the average. So we do 0.3 plus 0.2, we get 0.5 divided by 2, and I get 2.5. And it turns out that that's too small. So how do we calculate the standard error for the difference? And the answer is, we do the Pythagorean theorem. A squared plus B squared equals C squared, where C is the difference. So we take 0.2 squared plus 0.3 squared, and then we take the square root of that. So the square root of 0.2 times 0.3, oops, I got to square them. 0.2 squared times 0.3 squared, we end up with 0.06. Okay? So the 0.5 was way too big. The 2.5 was too big. It turns out that the difference is 0.06. Okay, now let's go back up here. Let's say I didn't know what was in the boxes. Okay, and I do my draws. So I do my draws. I end up with an average of 7 and an SD of 0.2. Or wait, I end up with an SD, and I use that SD to create my SE, and my SE is 0.2. And then you do your draws, and you get 6 with an SE of 0.3. Okay? We want to compare these to each other, and we're going to do that using subtraction. Which one of these goes in the middle of the normal curve? And the answer is neither. You subtract them, and you end up with 1 plus or minus 0.6. And that's where the normal curve is. 1 with an SE of 0.06. Now, that allows us to compare things together. So, a bunch of people go get their wisdom teeth out. They label their pain, right? The people who these people got the placebo and these people got the drug, right? The average pain for these people was a 7 out of 10. The average pain for these people was a 6 out of 10. Did the drug work? We don't know. We have to compare them. And that's where two sample tests come in. So what we would say is the null hypothesis would be what? That it did work, meaning the placebo is equal to the real drug. Okay? So the placebo pain was equal to the regular drug pain. The alternative hypothesis would say the placebo pain was greater than the drug pain. And the drug company is really hoping we reject the null. If we reject the null, then the drug company will be given permission to sell their drug as long as it's safe and passes all the tests and everything else. Okay? But they have to prove that it's more effective than nothing. And the weird thing about medicine is nothing is quite effective. Right? A lot of times when a doctor does nothing to you, where he actually does something, it tends to make you feel better. Which is why, you know, the doctor's always looking in your nose and your eyes and your ears. And you're like, doctor, I came in for knee pain. Well, that act of being a doctor and checking you out makes you think that he's more competent, which makes you heal faster, which is weird. But that's how placebo works. Okay, so now the question is, how do I set up this test? The scores were different by 1. Is that enough to say that it worked or it didn't work? Well, that's what chapter 27 does. Okay?